Hi, my name is Sokoy Celestine. Today we're looking at equilibrium of forces. Let us simply term these forces in equilibrium, where we know that force is anything that can cause or alter motion, while equilibrium will mean a state of balance or equal. So if we put this together, we can say that equilibrium of forces would simply mean a state of equal forces, where the forces acting on either sides are equal. So in today's class, we'll definitely look at introduction to equilibrium of forces, where I'll introduce equilibrium of forces in the best possible way. We'll look at moment of a force, moment of a couple, triangle of forces, center of gravity, and stability of objects. Introduction to equilibrium of forces. Like I said earlier, it is simply a state of equal forces. Equilibrium is the state of an object's quantity during which there is no change in the quantity of that object. What does this mean? If we look at the state of an object as a position, then there are forces acting on that object from either side. Yet that object does not move. We can say that the forces acting on that object are in equilibrium. An object is in equilibrium if the net force or resultant force on that object is equal to 0, which means forces acting on the body, let's say a box sitting on the ground, is pushed by two boys from both sides, and the box does not move. It means that the boys are pushing the box with the same force. It definitely tells us that if the forces are equal, the box cannot move. It means that the forces applied by the boys are equal. Now, what does this mean? And what happens to the body? We can have this in two phases. One, this means that all the forces acting on the body are different. From different sides are equal. They balance out. Now we can say that if we're looking at upward forces and downward forces, leftward forces and rightward forces, they are all equal. The body will not move. Then what will happen to the body? Two things will happen. One, we can have static equilibrium and we can have dynamic or kinetic equilibrium. Two, what happens to the body? One, dynamic equilibrium, where the body does not move. Let's take a look at this book sitting on a table here. The books are not moving. There are two forces acting on that body. One is W, downwards, which is gravity. The force acting, the weight on the body, gravity. Then it has an opposite reaction. According to Newton's third law of motion, for every action there is equal and opposite reaction. There is a normal reaction acting upwards. So the normal reaction force and the gravitational force are equal. That is why the book will not move. That is static equilibrium. Remember, we are looking at what happens to the body. The first one is that the body will not move. For a body to be in equilibrium and forces are acting on that body will not move if we are looking at static equilibrium. Then the other case we might have is when that body moves with constant velocity. Let us assume this to be a car that is moving. The car will move continuously with constant velocity, the same velocity. This necessarily means that the body or the car does not change velocity, which means all the forces acting on that body will remain the same. We call it kinetic or dynamic equilibrium. The forces acting on that body, on the car, remains the same. It does not change. That is why we have the word constant velocity. If you remember that we can define acceleration as the rate of change of velocity, basically the increase in change of velocity of a body. That is for acceleration. Or we can have deceleration as the decrease in change of velocity with respect to time. So if we look at this in terms of a tug of war, where we have the boys on this side and we have the girls on this side. Up here we are saying that the net force is equal to 0. Now we assume that the boys here are pulling the rope. They are pulling the rope with a total force of, let's say, 15 Newton. This one is pulling with 5 Newton. This one is with 5 Newton. This one with 5 Newton. I don't even know whether these boys are sleeping. Then we can assume that these girls here are pulling with a total sum of 15 Newton, 5 Newton, 5 Newton, 5 Newton. Nobody will win. It totally means that the forces applied by the boys will cancel out the forces applied by the girls. Thus, we have the net force, also called resultant force, to be equal to what? 0. This girl is completely unserious. She's doing something else. So back to what we were saying, the net force or resultant force is 0 when the forces are equal. We can have this case as mathematically. Let us look at this mathematically, where we say that the summation of the forces acting on both sides will be 0 because the forces are equal. Now, why do we have this mathematically? Remember that force is equal to mass times acceleration, and acceleration is change in velocity. Now we do not have change in velocity, which means our v automatically is equal to 0. Our v automatically is equal to 0. Then if we do not have change in velocity, like I earlier said, change in v becomes equal to 0. So if we look at this from this point down here, once we have f equal to ma and a is equal to velocity over time and v is equal to 0, it means that 0 will multiply every other thing. Then it brings us back to summation of force equal to 0. Moment of a force is something we experience every day. When we ride a bicycle, open the door using the door handle, we turn the tap heads, we screw a nail, we are exerting a force that gives rise to a turning effect. Now, if we look at this in a nutshell, it means that we are doing something, or we are applying a force that creates a turning effect. When you turn the door handle, you see that you are applying a force, then it turns. So in physics, we say moment of a force is the turning effect of a force about a point. That is usually a pivot, the turning point. Now, moment of a force is mathematically the product of a force and the perpendicular distance of the line of action. If we look at two factors that we must consider here, one is the force we apply. Two is the perpendicular distance of the line of action. Which means if we have to get the moment of a force, we are looking at the multiplicative effect of force and the perpendicular distance from the point of turning or from the point of pivot. Now, the unit for moment of a force is Newton meter. If we look at this using the principle of moment, which states that for a body to be in equilibrium, the sum of forces on one side must be equal to the sum of forces on the other side. Simply, the sum of anticlockwise moment about a turning point or about a point is equal to the sum of anticlockwise moment about that same point. It generally takes us back to what we said about the upward forces must be equal to the downward forces, leftward forces must be equal to rightward forces. Now let us assume and look at this diagram and look at this red line, the red thick line, as a meter rule resting on a knife edge, the triangular black shape here. Now it is possible for this to rest. One, if the moment on this side will be equal to the moment on this side. Now let us assume that on this meter rule we have two forces, F1 and F2. Let's assume we are tying a rope here, then we add a mass to that rope and we do the same here. They are perpendicular, or let's say this force here, F1, is perpendicular to the distance from here. Note this, this is the mistake most students make. The distance you are using is the perpendicular distance from where the force is applied to the center of, or to the point where the knife edge is situated. I go again. Moment of a force is the product of force times distance, the perpendicular distance. Now the force is that point where the mass is attached, while the distance is from that point where the mass is attached to the point where we have the center of gravity, or possibly where we have the knife edge situated. We have labeled A. Now the moment on this side would be F1 times A, while the moment on this side will be F2 times what? B. This sign here tells us that we have a perpendicular, that F1 is perpendicular to A, while this sign here also tells us that F2 is perpendicular to A. If the distance is not perpendicular to the force, we do not have moment of a force. Then you have to first of all look for the perpendicular distance, because before you can find the moment of that force. This curved arrow here tells us that there is a force acting downwards, and I believe you should know that this side is what we call the anti-clockwise side. That's if you look at your clock, how the hand of the clock moves. That's why, back to the principle of moment, we stated that clockwise moment must be equal to what? The anti-clockwise moment. So this side here now is the anti-clockwise moment, going in the anti-clockwise direction, while this side here now is going in the clockwise direction. So the moment on this side, clockwise moment on this side, which is the F1 times A, anti-clockwise moment, must be equal to what? F2 times what? B. Anyhow you want to put it, clockwise moment equals anti-clockwise moment, or anti-clockwise moment equal to clockwise moment. They must be equal for that meter rule to be in equilibrium. Let us look at this example here. A meter rule is pivoted at its midpoint C with a vertical force of 10 Newton hanging from the distance 30 cm from C. At what distance must a 15 Newton force hang to balance the ruler horizontally? If you look at this, we have the knife edge at C, then the distance from this point where this force is hanging is 30 cm, while on this side the distance from where this force here is hanging is 15 Newton. Remember what we said, force times distance must be equal to what? Force times distance. Thus we have 10 times 30 cm must be equal to what? 15 times what? Y. If you do all that mathematics, you have what? 300 equals 15y. Then divide both sides by 15. We have our y to be equal to 20 cm. It means that the distance from this point C to where the mass is hanging must be 20 cm before this meter rule can hang horizontally. We have another question here. If you look at this one, the distance provided for us here is 12 meters and the force applied is 10 newtons. Now look at it. Remember I said that the distance we are using must be the perpendicular distance, and the perpendicular distance is OQ, which is this. So we first of all have to use SOHCAHTOA to determine the distance OQ, then we multiply it with 10. That will give us the moment of the force. So that is what we have done here. We use cos theta equals adjacent over hypotenuse. So doing all that, we have our OQ here to be equal to what? 10.4 meters. So the distance from O to Q is 10.4 meters. Then we just apply the moment of a force principle, which is force times perpendicular distance. So the force is 10 Newton, the perpendicular distance is 10.4 meters. Then we have a moment to be 104 Newton meter. Remember, the distance we are using must be the perpendicular distance. We have the third question here where we have the knife edge at this point, then all the way down we have the meter rule. But now we are hanging a mass here, and we are hanging a body, we are hanging something here which we do not know the mass, E. Remember, this is going upwards, so this one now will serve as the anti-clockwise moment, while this one here now will serve as the clockwise moment. So for E here we have the force as E times the distance. Remember, the distance is from where it is hanging to the center of gravity. So we are multiplying 2.5 plus 0.5. If we do that, we are getting 3. So the distance for E, this force E, is 3, while the distance for 18 Newton is 0.5. So that's what we have done here, and we have gotten our E to be equal to what? 13.3 newtons. Thank you so much for this class. Our next, remember to call us or subscribe to, and also subscribe to our channel. Okay, in the next class we'll look at the following: moment of a force and the rest of them. Thank you so much.